Assalamualaikum and hi. We are from Group 1 today to present our lab report for Experiment 7, which is the Torricelli law. This is our group member, which is 4 people. Lim Zi Hui, myself, Norainun, Basyirah, Nurul, Afifah, and Afiq Danial.
This is our table of content.
For the introduction, our experiment is about the Torricelli theorem or Torricelli law. Is a theorem in fluid dynamics that explains the relationship between the velocity of non-viscous fluid flowing under the force of gravity and the liquid height in the container. The experiment demonstrating how gravitational potential energy is converted into kinetic energy in a flowing liquid.
So the objective of this experiment is to verify Torricelli's relationship by comparing measured and theoretical value of velocity. For this slide, you can see there is three equations. So we're going to derive equation 1, which is Bernoulli equation, into equation 2, Torricelli law. So in figure 1.1, we can see that it is a large reservoir, meaning that the velocity 1 is equal to 0. And also for the pressure, point 1 and point 2 is also equals to PATM. So we cancel out pressure 1 and 2. The reason why is because the pressure of point 1 and point 2, they exposed to the atmosphere. So we derive and we get equation 2 to calculate our velocity at the point 2. And Z2 is equals to 0, 2, because we set Z2 as our datum in this experiment. So we will get the formula, which is Z2 equals to square root 2 multiplied by gravity multiplied by Z1. So is equation 3. Here are the three equation, which is equation 4, 5, and 6. So equation 4 and 5 is the equation that we use to calculate the experimental velocity, and y is equals to the fixed height of nozzle to the ground, and also x is the maximum horizontal distance traveled. T measure is the drainage time, and also percentage error, we're going to get velocity theoretical minus velocity experimental divided by velocity theoretical multiplied by 100%. So this one is equation 6. So this is the experimental setup, where we can see there's the cylindrical cylinder with a drill hole, measuring tape, and also clay in figure 1.3. For the methodology, number one, the apparatus is set up based on the three different heights of stages, looking at figure 1.4. Number two, water will be filled into the cylindrical tank. Number three, height will be measured from the center of the nozzle to fluid at the surface of the reservoir. And number four, the whole of the cylindrical tank will be covered and stopped at the desired amount of volume of water. Number five, finger will be taken off from the hole. And number six, at the same time, the maximum distance will be marked by using the clay and the time will be recorded. Time will also be recorded when the water reaches to point x1 and x2. Number eight, the procedure will be repeated by using different volumes of water and at a different height of stages, H1 and H2, looking at figure 1.8.
For the discussion of the experiment, for question number 1 is about the selection on dependent, independent, and custom variable. For the dependent variable, the first one is initial water level, which is the starting height of the water in the tank. It directly affects the water pressure at the hole, which affect the speed and the distance water travel when it exits. Second one is the time taken for water to drain out. The long it takes to flow out from the tank, it depends on the water level and the speed of the water flow through the orifice. The independent variable, the first one is height of water from the nozzle to ground, which is the vertical distance between the orifice and the ground. It affects the time and the distance of the water trajectory as it exits the tank. Second one is maximum water trajectory distance, how far the water travel horizontally after leaving the nozzle. It depends on the initial water height and the height from orifice of nozzle to the ground. For the constant variable of our experiment, the first one is size of the hole on the cylindrical tank, which is the diameter of the orifice through which water exits. Keeping the orifice size constant ensure that the changes in water flow and trajectory are due to the other factor, not the variation in hole size. The second one is density of fluid. The density of the fluid used in the experiment. For a correct result, the density should remain constant as change in the density affect the flow rate and the pressure.
So for discussion, question number two, clarify on how you can relate the Bernoulli equation with Torricelli law for this case and show all the derivation and explain each step. So basically from Bernoulli equation, we can cancel out P1 and P2 due to P1 and is equal to P2, which also equals to P atmospheric pressure. And V1 will equal to 0 due to it's open to the atmospheric. Therefore, there will be no velocity. And then after that, we can simplify the equation so that Z1 equal to V2 square over 2G. And after we rearrange to get the velocity, we will get the V2 equal to square root of 2G Z1, which is Torricelli equation.
In this table, we can clearly see that when the volume of water increases, this causes the height difference of orifice to the surface of water in cylinder H increase. The more difference of height, the higher the velocity in theoretical. Hence, the theoretical velocity decreases from 2 liter to 1 liter. One fact is interesting is the different stage does not affect the velocity of water. This is because for Torricelli law, only the height difference between orifice to the surface of water will affect the velocity of point 2. Hence, there is no big significant change in velocity theoretical for a different stage at same volume of water. For example, the V of first stage at 2 liter of water is the same as second stage of 2 liter of water. In the experiment as in the first stage, second and third stage the velocity of 2 liter of water is the highest. This is because the maximum distance of trajectory distance is the highest for 2 liter water in all stages. The velocity decreases when the maximum water trajectory distance decreases from 2 liter to 1 liter. The highest velocity that we obtain is at the third stage with 2 liter water, which is 1.46 meter per second. In this table 6, we can clearly see that with this experiment has proven Torricelli's law. The percentage error of the velocity theoretical and velocity experimental is low. The highest percentage is at second stage at 2 liter water, which is 12.4%. The experimental velocity we obtain is slightly higher than the theoretical velocity.
For the last question is about the source of error and method to minimize the error. The first one is the error in measurement. The error may happen in measuring the height of the water level or timing the flow accurately. Method to minimize the error is use precise measuring tool, which is a ruler with a small gradation and a digital stopwatch to improve accuracy. The second one of error is non-ideal orifice shape. It is an uneven or rough orifice can cause turbulence and alter the water flow, leading to the inaccuracy. Method to minimize the error: ensure the orifice has smooth edge and it's perfectly circular. If possible, use a pre-manufactured orifice or polish the edge to reduce the turbulence.
Measures distance and travel and time. From the figure above, we can see that as the time increases, the distance of the water traveled decreases. This shows that for all the volume of water used, the velocity of the volume decreases as the time increases. And at T2, the water traveled at a distance of 0.6 cm, 0.53 meter, and 0.38 meter for 2 liter, 1.5 liter, and 1 liter of water, respectively. This is because the volume of water affects the depth of water. The greater the volume of water, the deeper the depth of water, and the higher the pressure and velocity of water spills out. Hence, this shows why water having volume of 2 liter have the furthest distance traveled.
For the safety procedure, we must wear appropriate equipment including lab coat, gloves to show and gloves if needed. Ensure the cylindrical cylinder is stable on a level surface to prevent tipping and spilling. The third one is keeping the experimental area dry and wipe up any spill immediately to prevent slip. Keep all electrical equipment such as a stopwatch away from liquid, and last one is carefully pour out any remaining fluid into the sink.
So in the conclusion, the Torricelli theory fits proven experiment. We can see that it is a theoretical and